Yeah, thank you. Alright, so good afternoon everyone. How are you doing? Everyone? Yeah? Okay, I hope you started the assignment or mostly almost finished it. Right, so today we'll keep it short, the so-called lecture-9 part. And then we'll go to introductions. Yeah, so today we'll just wrap up Module 1. So let's just take a look at some of the things we did. Right, so we formulated this ILP for the shortest path problem. Right. And we discussed that any solution to this system is not actually an SD path, but it contains an SD path. And that is basically because of this proposition that we just wrote down. And well, we did not prove it, so let's prove it. So how should we proceed? So we have a set of edges F. That set meets every SD cut, which means that its intersection with every SD cut is non-empty. And the claim was that the subgraph formed by these edges contains an SD path. Right, so how should we proceed? Any suggestions? Contradiction. Suppose not. Suppose this fellow does not contain an SD path. What does that mean? What can you say about the word as and T? They belong to distinct components in this graph. I don't know about the graph G, I don't care about the graph G, I care about this graph. This basically is the same as saying that in this graph, S and P lie in distinct components. Yeah? Say H and J respectively. I thought we don't need both, but it's just easier to write respectively. Let's say supposing this S fellow belongs to H and this D fellow belongs to J. Right? In this graph. So now what do? We should contradict something, right? We should contradict the only thing we have in life. Okay, so what is the cut you would like to consider? Partial of H. Right. Let C be partial of the vertex set of H. Is that what you mean? Yeah? A question is partial in which graph? Now there are multiple graphs floating around. There is a G fellow, there is this fellow, there is H and J. So partial in which graph? In the original graph, right? Because you want to contradict means every SD cut of G, right? That is the implicit point here. Right? So we will take the partial of this fellow in the original graph. Does that make sense? So whenever you have multiple graphs floating around, please specify which graph you are referring to. We should not have to read your mind because we will not read your mind. So we are looking at this cut in the original graph G, right? So this fellow H is a component. This is a component of this graph. It's not incremented, but it's okay. It contains this fellow S, right? But we are looking at its cut in the graph G, right? And we would like to contradict that F meets every SD cut. So actually, consider F intersection C. What can you say about this? Right? this is, it should be non-empty, but it is actually empty, which is a contradiction. Okay? Because if there were an edge in this set, if there were any edge, remember this is the cut C corresponding to this fellow. C is this. Right? If there were an edge in this set, that would be in C and that would also be in F. That would mean that this vertex would also be a part of the same component in this graph. But this is not in the same component. So observe that F intersection C is actually empty. A contribution. Yeah. Alright, it's a pretty straightforward proof. It's a kind of proof that you would expect in a more than a discrete math course. The reason I wanted to do at least one proof before you submit your assignment is so that you know the level of redundancy. So, yeah. I mean, it's not that long, but hopefully it is pretty clear. It's nothing ambiguous about it. Okay, so we're done. So the point is, because of this, if you consider any solution to this system, these constraints, we don't care about the objective function right now. If you consider any solution to this system, remember integrality is part of the system. That's exactly something that meets the proposition. Right? This constraint here guarantees that if you pick out all the edges whose xc is greater than or equal to 1, then that set of edges will meet every ST cut, and therefore that set of edges will contain an ST path. So every solution here what we mean is that xc is at least 1, then you interpret that as E belongs to P, or let me call it Q. Otherwise it is not counted. Otherwise E is not in Q. Every solution X corresponds to a set Q that contains an ST path. And now when you throw in the minimization, now you see that the optimal solutions will basically be shortest ST paths plus extra zero cost edges. See if you can write a proof of this, it's not very difficult. Optimal solutions are simply shortest ST paths plus extra, possibly extra zero cost edges. Right? These may or may not be there. Does everybody see that? You see that the shortest paths are precisely the ones that correspond to optimal solutions. In particular, if I give you an optimal solution to this system, which is entire ILP, then that is a set of edges, Q, and you take any ST path in that set, that is the shortest ST path. Yeah? So when you convince yourself of this, I'll put this as a DIY. And of course, feel free to discuss on Piazza in case you are not able to prove it yourself. Yeah?
Yeah, you think the fact that CD, the cost is positive?
Yes. We are definitely using the fact everywhere. The costs here are non-negative.
Why do we want to make this?
Can you repeat that?
Why do we want to make this? Like if we relax this,
Okay.
would we not be able to formulate this as that? We would still get.
So you're saying why don't we allow negative costs? Let's discuss that. So that's a good point. In the perfect matching case, we did not have any restriction. We allowed negative cost edges, but here we are not allowing negative cost edges. What is the reason for that?
You can loops or something, but we find that negative loops.
Well, if there's a negative cost edge, right, I can bump it up as much as possible. Right, so in fact, there will be no optimal solution only. For example, if my graph has any negative cost edge, you could give me a solution where the XC of this edge is 100. I'll make it 101. That's better. Right? So, if you allow negative cost here, then basically you have no control over, you can't even guarantee that this ILP has an optimal solution. You could explicit XC to be at most 1. Okay? So now what? Okay? So let's suppose we add the additional constraint that every XC is at most 1.
Like if we have a negative edge that's not part of the path. Like,
If you have a negative edge that is not part of the path,
like it can be SP path plus.
then I would still include it and I would get a shorter path because
Yeah.
that's another problem.
Not exactly.
Right? So there are issues that we run into. This issue doesn't arise in perfect matching at all. In fact, in the case of perfect matchings, observe that every perfect matching or maximum matching has the same cardinality. Right? Every maximum matching has the same cardinality. Also, every perfect matching has the same cardinality. So if you bump up, supposing you have negative cost edges in the perfect matching problem, let's say the minimum cost is 100 minus 100. I will just add 100 to every edge and things will still be okay, is that correct? In the case of perfect matchings, if I just bump up everything by, because every perfect matching has the same number of edges, if I just add a constant to make all my negative numbers disappear, I still don't change anything. Whereas here that is not true. Right? Because here the shortest path itself is defined as the minimum cost path. And the number of edges in the path, we don't have any control over that. And so there are some certain differences. In fact, if you allow negative costs, the shortest ST path problem is no longer that easily solvable. I would have to check whether it is LP hard or not, that is not clear to me. But I would have to, so if you allow negative cost edges, one thing that could happen is you could introduce negative cycles. And now I can, if I have a cycle, but of course what you are doing is you are bumping up by 1. So there is that thing. I'll have to think about what actually happens if you add this constraint. Of course, if you don't add this, then it's very bad. But if you add this, then you have some control over the situation. But I would still have to check what is status is. But that's a problem, right? It doesn't preserve the shortest ST path. Because supposing I have a shortest ST path, I have a minimum cost ST path that has 100 edges. And let's say there is, in my current instance, in the original instance, there's a minimum ST path with 100 edges, and there's a minimum cost ST path with 5 edges. Now do you see that in the new instance, one of them is no longer the shortest ST path because of the 100 edges, everywhere you added the same constant. This issue doesn't arise in perfect matchings. Right? So that is the crucial difference between these two. Anyway, so in general for the shortest ST path problem, we typically won't allow negative costs. Of course, the one way to look at why it makes sense is because generally this is distance, and distance are typically not negative, but that is a very practical reason. That's not the kind of reason that makes me happy. Yeah. So yeah, so definitely we are using the fact that edge costs are not negative in a lot of these arguments. Good. Alright. Any other questions, concerns? Yes.
Maybe why we add like constant cost in interval like not negative? Why is like problem is not
So think about it, if my original instance has two shortest SD paths, remember by shortest we mean minimum cost. One could be 5 edges, one could have 100 edges. The cost could be same. Now if I add a constant to every edge, the cost of the 100, do you see the point? That doesn't happen. Any other questions? Alright, so let's see. So that's the ILP for shortest path. Let's quickly write down in compact format. Right, so this is C transpose X, subject to. Now we have a matrix where the rows correspond to SD cuts and the columns correspond to edges. Right? So AX is at least one. Here this is the, I will give it a name. This is the SD cuts edge incidence matrix. This is non-standard, but it pops up here. So we'll just call it the SD cut edge incidence matrix. And I want my vector to be non-negative, and I want my vector to be integer. This is the all ones vector. Right, so that's the sort of compact format of this fellow. Okay. Yeah, so one DIY that I posted on Piazza yesterday was related to the other formulation that we had yesterday. Right, so one of the formulations that was suggested was, so this is just a particular formulation that we'll be working with. But in general, in SD path, S and T have degree 1 and every other vertex has degree 0 or 2. And we wrote down the constraints for that. And we incorrectly concluded that this actually captures exactly the SD paths. But that is not correct. And at least one of you answered on Piazza last night, the point is, you could also have additional cycles in the graph. Or you could just take an edge, and if you don't have at most one constraints, you could just take that edge twice. So you could just set the xe for that edge to be equal to 2. Then the sum here is 2, and the sum here is 2, set everybody else to 0. Right, so these are all 0. Yeah. So you could have these kind of things in addition to SD paths. So that was one issue. Of course, since it is a minimization problem, maybe it doesn't really matter because the costs are non-negative. I will just ignore this. I will still have a path. I will have a unique component that is an SD path, and I'll just pick that component. The other problem was that the way we wrote it yesterday was not an ILP. So Dipanjan has posted on Piazza about how to make an ILP using the same thought process. So please take a look. I have not yet taken a look. And see if you can come up with other formulations for the SD path problem. Right? So the formulation we will work with is this one. Because there is a lot of theory here that we will apply. But of course that doesn't mean that this is the only formulation that can yield a polynomial time algorithm using duality theory, blah blah blah. Right? So maybe there are other formulations, and maybe there is some nice theory there, I don't know what it is. So yeah, please do that. Any questions, concerns? Alright, if not, we are basically at the end of module 1 now. So what we have done in module 1 is we have talked about these two component optimization problems, perfect matches, minimum cost and choice maths. And we have written down the ILP formulations. If you throw away the integrality constraint, what you get is the LP relaxation of the problem. And the plan is to basically, one of the main goals of this course is to see how these problems can be solved. The original combinatorial problems can be solved using the theory of linear programming, which means we will drop the integrality constraint and still somehow make something good out of it. Right? But in order to do that, we will need the theory of linear programming. So module 2 onwards, for the next 2 to 3 modules, we will be focusing on linear programming. We will forget all this graph theory and all that nonsense. We'll just look at linear programming. Right? And that will be the goal for the next couple of weeks. We will conclude with duality theory, LP duality, and then we will come back to these common optimization problems and hit them with a hammer and solve them. Yeah? Okay, so that's all for today. Are there any questions or concerns before we start with the introductions? Anything you would like to ask, discuss? No, all good. Okay, so in that case, I will erase the board and we will start the introductions. And please introduce yourself, say some things about yourself that we wouldn't know otherwise will be. And maybe write your name on the boards so that we know who has introduced themselves. Thank you.